Case study 2.1 looks at exponential growth, exponential decay, an extremely versatile law of 70, which we'll see emerges out of the mathematics. The quantity Q that we're going to consider here grows at a constant percentage rate per unit time. In other words, 5% per year, 10% per year. And this leads through the mathematics to exponential growth. So when we look at this quantity Q, we look at the quantity delta Q over Q per unit time, and that is equal to a constant. In other words, 5% interest on your bank account per year is a constant. So we have the clear starting point for this calculation is delta Q over Q divided by delta T is equal to this constant K. But we can also rearrange this. We can express this as delta Q delta T, that is the change in Q per unit time, that's equal to this constant K times the quantity Q. So the rearrangement of this basic expression is a very important part of relating this fractional change per year to exponential growth. So let's look at how this is treated. First of all, we start by looking at delta Q over delta T in the limit of delta T going to 0. And that allows us to exchange the delta Q over delta T for the differential dQ dt. And this is very important because it allows us to use calculus. So let's look at this expression. We have the fact that dQ over Q is equal to K times dt by a rearrangement and recognizing that we can apply calculus to the time interval just as we can to the interval in dq. So the question then is, what do we do with this? And the important thing is that we can integrate both sides of this, and we can integrate this from the initial conditions to the final condition, which is comparable to integrating from the initial time t equals 0 to some time t in the future. But now let's look at the left-hand side of this. When we integrate dq over q, that's equal to the logarithm of the ratio of q at some time t divided by the initial value of q. That integral dq over q, which is essentially dx over x, is the most versatile integral in all of the chemical sciences, and we'll see it appear many, many times. So when we look at the right-hand side, we recognize that K is a constant, and that means that we can draw it out of the integral, and we can integrate dt from t equals 0 to some time t, and that gives us the simple relationship of kt for the right-hand side of this expression. But we can express this then as q at any time t is equal to q initially times e to the k times t, and therein lies the exponential representation of the time development of q based on a constant fractional increase per unit time. And so when we plot q against time, we see this classical shape of an exponential growth. And this is an extremely valuable way of calculating what happens in the future, as we'll see next. So let's apply this to the case of analyzing quantitatively what happens when Q changes at a certain fraction per year. So let's assume that we have a situation where the final value of Q is twice the initial value. And this turns out to be important because we can calculate a doubling time for any quantity that has this characteristic exponential growth, because that means we can equate log of q sub t over q sub naught as the log of 2 times q sub naught divided by q sub naught, which is equal to the logarithm of 2. Why is this important? Well, it's important because we can set this equal to k times t sub 2, which will indicate as the doubling time for this exponential growth. And that means we can calculate t doubling time immediately. That's equal to the log of 2 divided by k, and the log of 2 is 0.693, and so we divide that by k. Now what we want to do is take this expression and convert it into a way of calculating the doubling time for a certain percentage change per year. So we recognize that the percentage growth rate is 100 times the value of k, because k was delta q over q, as we will recall. So then we can recast this expression for the doubling time as our 0.693 divided by k, multiply the denominator and numerator by 100, and we come out with 69.3 divided by the percentage change. We simply divide 70 by the percentage increase per year, and we can immediately calculate the doubling time. Let's pick 7%, divide that into 70, and that gives us a doubling time of 10 years. But let's look at what happens when we analyze carbon release from China and the United States with this terminology.